In the previous class, we are discussing about the preparation of xenon fluorides. And we have seen that how we can prepare the xenon fluorides, and that by mixing directly the xenon and the fluoride and in a nickel tube in different conditions of pressure and temperature. And we have seen that how we are able to write the reactivity of xenons, fluorides, and we can also have discussed the chemical properties of the xenon the compounds, you can say, noble gases. Now we can discuss about the properties of xenon fluorides, we can say that. So we are going to discuss that the properties of xenon fluorides, the properties of, we can say that xenon fluorides, that is, we can say that xenon fluorides, we are going to write that, the properties of xenon fluorides. So we can write that all these xenon fluorides, doesn't matter it is difluoride, tetrafluoride or a hexafluoride, they all are colorless solids which sublimize at room temperature. So we used to say that all xenon fluorides, they are colorless crystalline solids and sublimize at room temperature. All the xenon fluorides, HCF4, HCF2, HCF4, that is, and HCF, we used to say that 6, are colorless crystalline solids, colorless crystalline solid, that is, crystalline solid which sublimates at room temperature. Which sublimates at room temperature, we used to say that this sublimates at room temperature, we can say that room temperature of 298 Kelvin. Of 298 Kelvin, we say that all are very good fluorinating agents. All are the good fluorinating agents. Fluorinating agents, we used to write that agents. So all will be the good fluorinating agents. We can write that all the xenon fluorides, they are good fluorinating agents. By that reaction, we can say that, suppose I write like this, that is, when the benzene is treated with, we used to say that HCF2. Then in that case, I got the product as, that is fluorobenzene plus, I got HF plus, I got xenon. So that is how all are good fluorinating agents. We can say that when they are heated with, the benzene is heated with, that is HCF2, we get the product as that is fluorobenzene, that is formed in the reaction, that is fluorobenzene is formed in the reaction, as well as we say that it is fluorobenzene, HF, and the xenon is formed in the reaction. So they all are very good fluorinating agents, we used to say. Next is, we'll say that they are easily hydrolyzed. We can say that they are easily hydrolyzed. We can say that they are easily hydrolyzed with water. Hydrolyzed with water. All of them can be easily hydrolyzed with water. So all the xenon fluoride, the xenon difluoride, that is tetrafluoride, and the hexafluorides. So all these xenon fluorides, they easily hydrolyzes with water and even with the moisture. And even with the moisture, we can say that. So even the moisture is present, then also they will get hydrolyzed. Even with the moisture, we used to say that. So if a traces of water is present, then also they will get hydrolyzed. So let us check what will be the hydrolysis product is. So in hydrolysis product, I'll write that HCF2 will react with water to form, that is, we'll write that HCF2 will react with water. In this case, the reaction of water, we can compare the reaction of water of all of these, that is F4, when it reacts with water, what will happen? Let us check. And when we'll write that it is hexafluoride, that is HCF4, when it reacts with water, let us check what will happen. Now in first case, we used to say that it will form xenon plus HF plus, we used to write that O2. But in case of this, so here what happened, it shows that it is in +2 state, convert into the 0 elemental state, that is electron is gained in the process. So it is going to act as a oxidizing agent. But it is HCF4 which disproportionate. HCF4 actually disproportionate in that, right? So this shows a disproportionation reaction. HCO3 is formed, HF is formed, and O2 is formed in the reaction. Whereas in this case, we used to write that HCO3, that is oxidized. That in this case, it is not an oxidation process because the oxidation state, this is HCF6, this is HCF4. So this is HCF4, this is HCF6. So when it reacts with water, it will form HCO3 will be formed in the reaction and HF is formed in the reaction. That is how it shows the oxidation process. So let us check how the oxidation process is. So this will be the oxidation process in this case. In this case, you can write that the oxidation process is like this. That is 2HF, we get that. And we get that O2 and we'll write that HC is formed in the reaction. That is how I can write the balanced reaction, whereas I know that this shows the disproportionation in this case. So this reaction shows disproportionation. Disproportionation in this case. So we can write that it is HCF4, which shows the disproportionation on hydrolysis, but not the HCF6 or HCF2 is. So we can write the reaction as, we can say that it is 4, we can write that it is, we can write that HF we required is, that we can write that it is 12H2O, so we can write that it is, HF is 12HF and we'll write that HCO3. So we get that thrice of this will be formed, we'll write like this. So thrice of HC we get that it is, we'll write this as HCF that is 4 going to be converted into, that is, I can write this as 6 HCF4, then I can write this as twice. So that is xenon which is formed, that twice this will be formed, we get that it is 6 this and thrice of O2 what I got is, and the fluorine is, that is what we are having, that is fluorine is, that is 24. So I got this as 24HF. So that is how we are able to get the balanced reaction of these R. So that is how we get that in all these cases we know that this is a gas, this is a liquid, what we get, this is also a gas, this is a gas, HF will be a liquid, that is due to hydrogen bonding, this is a solid what we get, this is also we say that xenon gas, here it is liquid what we get, this is a solid what we are going to get in this reaction, H2O that is liquid what we have used, this is also liquid, here we have used these as a solids. So these are all what we have used, they are in solid state, we used to say that. So that is how we are able to write that, and you can write that if we are writing this liquids, that is an aqueous condition, we can say that. Better to write it as aqueous rather than we are writing liquids, because it is in water. So we can write this as aqueous HF we can write, but it is in, that is not exactly in liquid state, that is dissociated in water. So that is how we can write that the hydrolysis is, now I can write that the third one, that is called the partial hydrolysis. The partial hydrolysis of, that is, we can write like this, that is partial hydrolysis. So the partial hydrolysis is the HCF4, when it is partially hydrolyzed, that is, it will be like this, HCOF2 is formed, plus twice of HF will be formed in the reaction. So that is the partial hydrolysis, what I can write is, but the partial hydrolysis of this is very difficult, it is carried out at minus 80 degrees centigrade. So the partial hydrolysis of HCF4 is carried out at minus 80 degrees centigrade, but the partial hydrolysis of HCF6 is easy. So we used to write that the partial hydrolysis of HCF6 gives the oxyfluorides. So it gives the oxyfluorides, these are the oxyfluorides, gives the oxyfluorides of xenons. Oxyfluorides of xenons are formed in the reaction. So if the temperature is not mentioned, then in that case I'm not going to write the partial hydrolysis of HCF4. So this is of HCF4, then I can write that for HCF6. When we add one water molecule, we used to get that it is, this is complete hydrolysis what I have written. So here it is a complete hydrolysis, what I have written is, that is the complete hydrolysis I have written here. If it is partial hydrolysis, I am going to write like this, that is HCOF2 plus twice of HF will be formed in the reaction. Then I can write that HCFO2, this will again react with water to get converted into HCO2F2 plus twice of HF. Then this again react with water to form that is HCO3 plus I'll write that it is water, that is HF. Twice of HF will be formed. So this is how we used to write that the partial hydrolysis, the product of the reaction we get in the partial hydrolysis is. So these are the product of reaction with the partial hydrolysis is HCO3, which is formed is a colorless, we say that explosive solid, and these are like this. We used to say that HCO3 formed is a colorless explosive solid, colorless solids. That is, we used to say that it is a colorless solid which is explosive in nature, which is we used to write that explosive in nature. In nature, we used to say that, and that is we used to say that the HCO4 and HCOF4 is a colorless volatile liquid. Is a colorless, we used to say that colorless volatile, that is a liquid. So that is how we are able to write that about the nature of these intermediate compound on the partial hydrolysis, what is we are getting. So that is how we can write that they are good fluorinating agent. What the product on the hydrolysis is in all the cases. We can write the product of hydrolysis. Next we can write as the reaction with hydrogen. If we write the reaction with hydrogen, we can write like this. So next we can write is the reaction with hydrogen. All react with hydrogen to form xenon and hydrogen fluorides. So we can write that the reaction with hydrogen is. So we used to write that next is that is reaction with hydrogen. So if I write that reaction with H2, so I'm going to write that the reaction with H2 is all react with that is HCF2 react with hydrogen to form that is xenon plus twice of HF. So that is how we can get that reaction with hydrogen. So similarly, I will say that similarly we'll write that HCF4 and HCF6 right also forms that is with hydrogen. We used to say that that is plus hydrogen will give us that is xenon plus HF, and we are able to balance the reaction. With H2 they will give that is the xenon and HF. So all react with hydrogen to get converted into the xenon and the hydrogen fluoride. So all will react like that. Next we can write that is a reaction with NaOH. So reaction with we can write that is NaOH. What is the reaction with NaOH is? So we used to write that the reaction with NaOH, it is first that is HCF2 will react with NaOH because it is an alkali by which they are going to react. So HCF2 when react with NaOH, we used to say that it convert into Hc. It will get converted into Hc plus NaF plus we'll write that O2 plus H2O is formed in the reaction. So let us write that the twice of NaOH I'm going to write that. Then we'll have water and half O2. That is how the reaction is. That is NaF, which is formed in the reaction. So it will react with NaOH like this. HCF4 directly doesn't react with NaOH. So we'll say that in case of that is, we say that the HCF4 and HCF6 does not directly react with NaOH. So I can write this as HCF4 and HCF, we used to write that 6 do not react directly with NaOH. Do not react directly with NaOH, but they can react like this. They do not react directly with NaOH, but they react with NaOH in the form of, if they are in form of oxides like this. Even this reaction is very slow. The reaction is slow, whereas the tetrafluoride and the hexafluoride does not react directly, but they react as. But we can say that, but they react like this. We'll say that, but HCF4. If we have HCO3 when react with NaOH, then in that case it is a basic medium. What we are going to write in basic medium, it forms a salt like this. That is NaHHCO4 is formed. So like this is formed. This is called sodium xenate. So we got that sodium xenate is formed in the reaction. So this is going to form, the sodium xenate is formed in this reaction. This is sodium xenate which is formed in the reaction. This sodium xenate again react with NaOH. So NaHXeO4, we used to write that NaHXeO4, that is a sodium xenate, again react with NaOH. It again react with NaOH and form a complex, that is Na4XeO6. So I got that Na4XeO6 is formed in the reaction. This is the complex which is formed in the reaction. So I got like this. That is the complex which will be formed in the reaction plus Xe plus O2 and H2O is also formed. Xe plus O2 plus H2O is also formed in the reaction. So like that we used to write that it will form the product like this. So that is how we can write that the product is. So this is how we get the product in the reaction is. So the product which is formed is called the sodium perxenate. This is called the sodium perxenate. This is called sodium perxenate is the product of the reaction we used to write is. So that is what we get the product of the reaction is. That is how we are able to write the product of the reaction in this case is with NaOH. So that is how we are able to write that the NaOH is reacting with not directly with HCF4 and HCF6, but it reacts with HCO3 to form the xenate, and that xenate react to form perxenate. So that can be formed in the reaction. Next we can write is the decomposition reaction. So if I write that the decomposition reaction, so we can say that the decomposition reaction of that is xenon fluorides. So we used to write that it is only hexafluoride which decompose on heating and form hexa tetrafluoride and xenon difluoride. So it is only this which decompose to form that the tetrafluoride, difluoride and the fluorine is liberated in the reactions. So we get that fluorine liberated in the reaction is like this. But the tetrafluoride and the difluoride does not decompose. But we say that xenon difluoride and xenon tetrafluoride do not decompose on heating. Do not decompose on heating, we used to say that. So it is only the hexafluoride which decompose on heating, forming the xenon difluoride, and that is the tetrafluoride. But the tetrafluoride and the xenon difluoride does not, that is decompose on heating. So that is how we can write the decomposition reactions of these. Next we can say that the reaction with Lewis acids. So we will say that the reaction with Lewis acids. If we write the reaction with Lewis acids, we can write like this. Lewis acids. Then we are going to write the reaction with Lewis acids like this. So the reaction of xenon fluorides with the Lewis acids we can write like this. With the fluoridine acceptor, xenon fluoride, that is, we can say that the xenon fluorides reacts with xenon fluorides reacts with the fluoridine acceptor. Fluoridine acceptor, that is Lewis acids. Lewis acids, because they are fluoride ion acceptors. So it reacts with the fluoride ion acceptors, they are Lewis acid, to form a cationic species and to form, we can write that acceptor to form, we used to say that Lewis acid to form cationic complexes, that is to form the cationic species, and fluoridine donor to form fluorines. Cationic species and the fluoridine, that is we say that fluoridine acceptor to form the cationic species, and or you can write that cationic and anionic species and anionic species. So let us check that the fluoride, xenon fluorides react with fluoridine acceptor. They are the Lewis acid by which we are going to write the reaction. So if I write that HCF2 when it reacts with suppose PF, you can say that 5. then it forms that HCF and PF6 that is negative. So that is what we are writing, that it is a fluorine acceptor. This is a acceptor and this is the fluorine donor. This is the fluorine donor, what we used to say that, and that is the fluorine acceptor S. Next we can write that we can write the HCF4. When it reacts with another Lewis acid, you can take any Lewis acid, doesn't matter. Then in that case, that is antimony sulfide, there is a very strong Lewis acids. In that case, again it will be a fluorine donor. So we got that it is a positive charge on this, the cationic complex, and SbF6 that will form the anionic complex, like that. We are able to write that. So they will react with the acceptor. This is a fluorine acceptor, that is a Lewis acid, and the fluorine donor, they itself are. So we can write like this. And we used to say that these HCF6 react with the metals. So they react with the metal that to form a complex M. I will write here, that is M. The metal it is. It will react with the metal to form the complex that is M HCF7. They will react with that. They react with metal fluorides, we will say that. They will react with metal fluoride to form M, that is HCF7, we will say that. So in that case, I'm going to write this as negative and this as a positive charge, which will be forming there. So in this case, the metal should be monovalent, and that monovalent metal is the metal which is here. In this, the metal is, metal M is, that is sodium, potassium, rubidium or cesium. These are the metal which will be present in this case. So that is about that the reaction with the Lewis acid is. So that is the reaction with the Lewis acid, and that is how we are able to predict those reactions. Now we can write that these are the reactions which are important for us. These are the important reactions of xenon and xenon fluorides. Next we can write the uses of xenon, that is noble gases. So other important part for the noble gases is their uses. So let us write first the uses, then we'll check what are more we can write that about these xenon compounds. So we'll say that that is uses of noble gases. So I'll write that for the uses, that is helium is a non-inflammable gas. Is a non-inflammable gas, that is flammable gas. And it is lighter gas. We can say that it is a lighter gas. So it is a very light gas. That's why it is used in the meteorological balloons. Generally in the meteorological balloons we use the helium. It is not non-reactive and it is inflammable. So it is a light gas. So it is used in the helium is used in the gaseous nuclear reactors. It is used in gas-cooled nuclear reactors. So it is used in the gaseous-cooled nuclear reactors. So it is used in the nuclear reactors because it for the cooling effect. We know that that is the boiling point of helium is 4.2 Kelvin. So its boiling point is very low. So it is used in the gaseous cooled nuclear reactors. So this is used in the gaseous cooled nuclear reactors, we can say. Next we can write is the liquid helium. So we can write that liquid helium is having a boiling point of. So liquid helium has a boiling point of that is the boiling point of 4.2 Kelvin. So it is used in to make the cryogenic conditions, because the boiling point is so less. So it is used as a cryogenic agent in the reaction at low temperature. So it is used as a cryogenic agent. Cryogenic agent means that is the agent which will which can make the temperature very less. So it is used as a cryogenic agent to generate the conditions of low temperature. So cryogenic agent to generate the low temperature. To generate the low temperature in the reactions. The low temperature in reactions, we can say that. So that is a cryogenic agent. It is used as a cryogenic agent because of its very low melt, that is boiling point. So it is used as a cryogenic agent. Now helium is used to produce, that is powerful superliquids. So helium is used to produce. So we used to say that helium is used to produce that is produce the powerful superconducting, because the temperature, the boiling point is very low. So it is used to produce the powerful superconducting magnets. Powerful superconducting magnets. Superconducting magnets, you can say that. Magnets, as its boiling point is very low. So it is used for producing the superconducting magnets. We know that for NMR and MIR, that is for NMR spectroscopy, NMR and magnetic resonance imaging. NMR is nuclear magnetic resonance and MRI is magnetic resonance imaging. So it is used in NMR and MIR spectroscopy. So that is used in that to make that superconducting magnets. Helium is a very important compound. Now helium is used to dilute oxygen. We know that helium is used to dilute the oxygen, which is dilute the oxygen. The concentration of oxygen, that is O2 in air, that is carried by the scuba divers. Carried by scuba divers. Right? Divers, we know that. So the sea divers, they used to carry the oxygen. So that oxygen, the oxygen is diluted by that, we used to say that, by helium, because it is non-reactive gas and it has very low van der Waals forces also. So that is how why we are using that helium in that case, in dilution of oxygen. Next we can write is, that is argon. Neon bulb are used to discharge tube and fluorescent bulb. Neon is used in the discharge tube and fluorescent bulb. So discharge tubes, that is glass tube, we know that, and fluorescent bulb. Fluorescent bulb. So the fluorescent bulb and the discharge tube, they are filled with the neon, that is neon gas. So that is the use of neon gases. Argon provide the inert atmosphere at high temperature. Argon provides the inert atmosphere at high temperature. Inert atmosphere at high temperatures. Atmosphere at high temperature, we used to say that. Because sometimes what happens in welding purpose, we won't require the oxygen, we require the inert gas. So high temperature in metallurgical process, that is, and in metallurgical process, we used to say that in metallurgical process, that is in welding, and in welding we know that in welding, etc. we say that. So we used to write that, and it is also filled in the, that is electric bulbs. So it is welding of metals, or obviously it will be the welding of metals, we say that, welding of metals, or even the alloys, we can say that, alloys, we used to say that. And it is also used to and filled in the electric bulbs, and also used to be filled in, it is and also filled in electric bulbs. Electric bulbs, we say that. So that is the use of argon, we can say that. Then we can write that, we used to write that the argon, it is also used in laboratory for handling the substance which are very sensitive to air. So that substance which are very sensitive to air, then they are kept in the atmosphere of argon. So it is also used, the argon is also used for handling the substance which are substance in laboratory, in lab, which are sensitive to air, so they are kept in the atmosphere of sensitive to air, so they are kept in the atmosphere of argon. So these are the main use of we can say that noble gases, but there is no significant use of krypton and we can say that xenon. So we can write that, but there is no significant use of we can say that significant use of krypton and xenon, but they can be used to fill in the electric bulbs, but they can be used to fill the electric bulbs, that is how we can write that. So these are the important we can say that uses of those noble gases. So these are important uses of noble gases are, and that is about what we required about the noble gases. Now we can read that we can compile that what are the compounds we have studied for the noble gases, about those their hybridization and their structures. So I'll write that the structure and geometry of next we can write is the structure, geometry, hybridization, shape of and you can write that bond angles of compounds of noble gases. As we know that already I have told you that we have discussed that part in chemical bonding, but we'll write that few compounds and their structure and we'll write their geometry of noble gases. So I'm going to write that part so we can make a table of that, and if required we can make their structures. So I'm going to write the table of those compounds. I'm going to make the table of those compounds. So I'll write that we'll make a table, that is serial number. We'll write that the molecular formula. I'm writing that. Then I'll write that hybridization. Then I'll write that it is geometry, shape. Then I can write that bond angles. So bond angles will only write this definite bond angles. So we are going to make this table, and I'm going to write that what is the structure and geometry I'm going to write for the noble gases. So we are going to write that table now. Molecular formula, we are going to write the hybridization, we are going to write the geometry, we are going to write the shape, and we are going to write the bond angles. Suppose I write that is for, I'm going to remove this part. So let us check that in case of, I just write that how we are going to make it. Just take one example. Suppose I have HCF2. In HCF2, we know that in HCF2 what will happen? There are 8 valence electrons, 2 are bonded, 3 lone pairs, S, P, P, P and P. So 1, 2, 3, 1 and 1 will be D. So the hybridization is sp3d hybridization. So in this case, I'm going to write that the hybridization is sp3d. The geometry is trigonal bipyramidal. There are 3 lone pairs, so I'm going to write that linear. The bond angle is 180 degree. That is the bond angle what we have. So that is what I'm going to write here. So that is how I'm telling that we can write for these molecules, how we are going to write that, the structure and geometry of these molecules. Next I can write is for HCF4, then I am going to write for, we'll check that how many molecules we can write is, we'll just make that like this. So I'll write the HCF4 means Hc have 6, that is 8 valence electron, 4 are bonded with a single bond, 2 lone pairs, so sp, p, p3 and d2. I'm going to write that it is sp3 d2 square planar, that is octahedral. I'm going to write that octahedral geometry, square planar, I have that, and 90 degree bond angles. There are 4 90 degree bond angles. The lone pair will be placed on the top and the bottom position. That is how I can write that it is structure S. Next I can write is, that is HCF6. If I write HCF6, then in that case I'm going to write that is 2 more fluoride will be like this. So P, D and D. One lone pair is there. So I'll write that it is sp3 D2 hybridization. It is octahedral. So I'll write it as geometry is distorted octahedral. So it is, I'll write that it is, we'll say that if I check, I'll get like this, that is sp3d. So pentagonal bipyramidal it should be, but pentagonal bipyramidal are very less number of compounds. So you are going to predict it like this, sp3d2. I'll write this as distorted octahedral. Distorted octahedral. And in this case also I'll write that distorted octahedral. Distorted octahedral, I'm writing that octahedral. But the bond angle is not 90. They are not 90 degree. The bond angles are less than 90 degree. So the bond angles will be, that is, we'll say that it is not 90 degree. And the structure of HCF6 is like this. Though I'm going to write that HCF6, one fluorine will be like this, other fluorine will be like this. That is how the fluorine are placed in this. Other fluorine is like this, one of the fluorine will be like this. Then I'm going to write that one fluorine will be like this. So I'm going to write that this is the square planar pyramid. The square planar pyramid is like this. The square planar pyramid, and at the bottom also we'll get one more pyramid. Then the lone pair will be placed at one of the face of the pyramid is. Out of 8 faces, one of the face will be accommodating that lone pair. So it is called distorted octahedral. Distorted octahedral is the shape of that. So that is how we get that it is distorted octahedral. So I'm going to write that it is distorted octahedral. So it is important for us. So you just write that here. That will be important for us. That the third one. What will be the structure we have? Now I can write that HCO3 will get that it is sp3, that is, I will say that tetrahedral. So I'll write that it is tetrahedral. Then in that case, I'm going to write that it is pyramidal. It is pyramidal and bond angle is less than 109.28 minutes because that presence of lone pair. Next I can write is, that is, we used to say that HCOF4. And in that case, I'll write that HCOF4 will be like this. Hc, that is having 8 valence electron, double bond O, then fluorine are 4. We'll get that it is 4 plus 1, 5, 1, 6. sp3 d2 is the hybridization. So I got that it is sp3 d2 is the hybridization. So it is octahedral, but we write that it is, we say that square planar pyramid. So square planar pyramidal is, pyramidal is the, right, we'll write that is the shape, and less than 90 degree will be the bond angles. Because due to that repulsion, if one of the position there is a lone pair, there is no lone pair in this, it will be like that, na? So here it will be like this, that is double bond O, and we'll get that one fluorine here, other fluorine here, then we'll have that one fluorine here, other fluorine will be here, and at this position there will be a lone pair. If there is a lone pair, then bond angle on the top side, that is due to the repulsion, lone pair bond pair repulsion, the bond angle decreases. Next I can write is, suppose I'm having that is HCO2F2. So HCO2F2, it will be like this. Then O2F2 is like this. Then 1, 2, 3, 4, 5. We are going to write that it is like a seesaw shape. So I'm going to write it as that is sp3d is the structure that will be, that is trigonal bipyramidal. Trigonal bipyramidal, we used to write that pyramidal, and that will be the seesaw shape. Seesaw shape will be the shape. So we'll write that the bond angle is neither it is 90, less than 90 and less than 120. So less than 90 degree and less than 120 degree due to the presence of fluid. So we can write that. Then we can write that it is HCO3. We have already written that. HCO, that is F2. So if I write that HCO F2, then in that case I'm going to write that it is like this. So HC, there is a lone pair, 8 lone pairs. O, it is like this, and F2 is like this. The 2 lone pairs are there. So in that case I'm going to write that the option, and this will be placed at right. So we'll write that it is 1, 2, 3, 4, 5. So sp3 dehybridization. So this is sp3 dehybridization. Then I'm going to write that trigonal bipyramidal is the geometry of that. So trigonal bipyramidal, and it is we'll say that it is, we are going to write that it is T shape, the T shape, and in that T shape we are going to write that it is less than 90, that is less than 90 degree, but there is no 120 degree in that. So we can write like that. So these are the structure and geometry as well as the bond angles in case of the compounds, what we get in case of these right elements of the 18th group. So that is all about that geometry and shape of elements of the 18th group is. So that is about the element of 18th group what we have to discuss, and that is how we can we have seen that their geometry, their shape, how the preparation, as well as we have seen that their properties, their reaction with alkali, their reaction with the acids, and all. Acid means we are talking about Lewis acid. So all we have discussed, and this is all about we used to say that the noble gases is. So this is all what we required in the noble gases is. So that's all in this class.